All right, chapter 10, section 6, segment relationships in circles. As the name suggests, we're going to be dealing with pieces of segments as they relate to each other within or around circles. And I just want to point out at this point that this is going to be a subtle difference from section 5, where there were angle relationships in circles. In that in section 5, all our answers dealt with some sort of degree measurement in regards to angles. In this section, we're going to be talking about segments, so we're talking about length and or distance. Okay, so you're going to see some kind of fundamental changes right there. Also on how it's going to be expressed and shown in a diagram. So I'll make sure I break that down as we work through it as well. In this clip, we're going to talk about 3 theorems that basically talk about how segments can interact with each other in or around a circle. And there's going to be a formula on how to solve for segment length in each of these theorems. And I'll break down how they're going to be translated. What's going to be important to understand here is that as we look at the letters in the formulas, the letters actually don't matter as much as understanding what objects are going to be there and what I'm going to be looking for to plug into those spaces. All right, so this first theorem, the segments of a chord theorem. I want to emphasize here again that I'm never going to ask you on a test to define or to name a given theorem or formula or anything like that. So understanding the name is far less important than understanding what it does. And so here's what we see here. In this green asterisk point that I make here, if I kind of break it down a little bit more in plain English, is that if 2 chords, basically a segment that is completely that contained within a circle where its endpoints are on the circle, if 2 chords intersect in a circle, like we see here in this diagram, it makes this little X on the inside of a diagram, the products of their pieces need to be equal. The products of their pieces are going to be equal. So breaking down what that means, a product simply means the solution to a multiplication problem. And when I'm talking about the product of their pieces, I'm basically multiplying together the lengths of the pieces of each chord. So what does that mean? So as you see here, I have 2 chords. I have chord AB and chord DC. Chord AB and chord DC. They cross each other at some point E in the middle of the circle. It does not have to be the center of the circle or anything like that. So this can happen anywhere. It just ends up with this X somewhere in the middle of the circle. What does it mean by the products of the pieces? Well, I break it down with these letters, but the letters are not really important. What's going to be more important is understanding what pieces multiply by which. Here's how this theorem breaks down. If I look at one of the chords, like say chord AB here, it's split fundamentally into 2 pieces by the other chord, chord AE and chord EB, or BE and EA. It doesn't really matter the order of the letters, but anyway, it's fundamentally split into 2 pieces. If I were to multiply the lengths of those pieces by each other, whatever this length A to E was times whatever the length from E to B was, that needs to end up matching the same product between the 2 pieces of the other chord. So this chord, CD or DC, however you want to describe it, is also fundamentally broken up into 2 pieces, DE here at the bottom and EC here up on the top. Whatever those lengths multiplied by each other need to match the multiplication product of the other 2 pieces. That's what this theorem breaks down. Any 2 chords, regardless of the letters involved, if I take the 2 pieces of one chord and multiply them by each other, they're going to have to equal the same product of the 2 pieces of the other chord involved. And the fact that they're represented by these letters is just really unique to this diagram that we're shown here. And what you'll see, we'll deal with this example in the next clip, but what you'll see for this example is that obviously the letters are different, and that's okay. What's still fundamentally going to happen here is I'm going to have 2 chords that are crossing each other on the inside of a circle. And so if I look at each chord individually, say chord ML going up and down here, and then chord KJ going left to right, if I were to break them into their 2 pieces and multiply those pieces by each other, so MN times NL, that's going to have to equal KN times NJ. So again, the letters are not going to matter as much, but what's going to matter is understanding that it's going to be the piece. So like on one side of the equation, that's going to be one of the chords, and each of those multiplications, that's going to be the 2 pieces of that chord. On the right side, it's just the other chord and its pieces. So piece times piece of chord 1 is going to be equal to piece times piece of chord 2. So if that phrasing helps you a little bit more, write that out in your margins or in your notes, whatever you need to do. And again, we'll work through this example. This will be one of the more complicated examples that we do, but we'll work through this example in the next clip. So theorem number 1. If I have two chords that intersect, two segments that cross each other inside of a circle, the pieces of one chord multiplied by each other are going to have to equal the pieces of the other chord multiplied by each other. All right, theorem number 2. Theorem number 2. What happens if the segments intersect outside of the circle? You see kind of the same logical progression here that we saw in section 5, where I could have angles on the inside or outside of the circle or on the circle. Okay, we're seeing the same thing here with chords, right? So now I'm getting two segments that cross on the outside of a circle. And fundamentally, it creates what we call secants, right? So just to break down the terminology, A to B right here, that is a chord. That's a segment with endpoints on the circle itself. As soon as I extend it beyond the circle, I have created what's called a secant, right, to break down the name of the theorem. So the whole secant here would be secant B to E, or E to B, however you think of it. And then down here, I have the same sort of thing. I have another secant, right, D to E, but part of that secant is the chord CD, right, just to break that down. All right, so what does this say? Fundamentally, there's a different formula now for solving for segment length here. And it kind of breaks down like this. I color coordinate it here, but it breaks down as follows. I have two segments, the one on top here and the one on bottom. And they cross each other at this outside point. Well, according to this, the outside piece, whatever length it is from A to E, and then I'm going to take that length, I'm going to multiply it by the length of the whole segment. So outside piece times the whole segment. And that's going to equal the outside piece times the whole segment. Okay, so the way this breaks down, the distance from E to A times the whole distance from E to B is going to equal the distance from E to C times the whole distance from E to D. Again, letters are going to be less important here. It's going to be more important to understand which pieces multiply by each other. So again, I kind of write it out in plain English here. External piece times the whole segment is going to equal external piece times the whole segment. And well, again, we'll do this example in the next clip. But you'll see that obviously there are going to be different letters, different names for the given points. This one will be a little bit more straightforward because we're going to get some explicit numbers in there. But essentially, it's going to be breaking down to like, all right, I'm going to have the outside piece, for instance, R to P, times the length of the whole segment from R to Q. So that will involve some addition of pieces in there. And then the other segment, I'm going to have the outside piece, R to S, times the length of the whole segment from R to T. So this theorem is going to break down as outside piece times the whole segment is equal to outside piece times the whole segment. That's theorem number 2. Theorem number 3 is actually just going to be an extension of this theorem, because we're still going to end up with an intersection of segments on the outside of the circle. So fundamentally, we can still apply this. So if you're the type of person that doesn't like to have a lot of formulas, technically we can just stick with the two that we've already covered. Whether it's intersecting on the inside or on the outside, it's going to be one of those two options. But this third formula is just going to break down one of the special case scenarios that we could technically get here. What happens is there a unique set of circumstances here if I have the intersection of two segments on the outside of the circle, which is still happening here. But what happens if one of those segments happens to be a tangent? In other words, it doesn't pass through the circle like a secant does. It simply glances off the side. So if I were to extend this off into forever, it would just never touch or go through the circle anymore. Well, it's really just the same exact formula. Okay? But what's going to happen here, particularly for this tangent piece, the outside piece of this segment happens to also be the entire segment. So if I were to treat this like the last theorem, I would look at this first segment and I'd say like, all right, well, outside piece is e to a. I'm going to multiply that by the length of the whole segment, which just also happens to be e to a. And so if I do EA times EA, that's where the fact that I get this formula where I get that tangent segment squared comes from. Again, this is really just an extension of the last theorem. It's just that in this case, the outside piece and the whole segment are one and the same. So when I multiply it by itself, that's why it becomes squared, like we see here. And then the other side of the equation, you'll notice this is just like the last theorem. Outside piece, e to c, times the length of the whole segment, e to d. Right, again, letters not important. More important is understanding the pieces that multiply by each other. So this is just a unique extension of the second theorem. It's what we would call a corollary. Okay, so this is going to kind of conclude our first clip on the theory and the explanation behind what we're going to be doing. In the next clip, we're going to cover a couple of examples that apply these theorems, and we'll see how they actually get worked out on paper. And we're going to work on basically looking at what kind of variations we'll see in the examples on big ideas and or on a test, kind of representing how we would apply algebraic phrases versus explicit numbers. And we'll look at that in the next clip. So that'll conclude our first clip on the theorems.